Good afternoon. We are going to start the last session of the Congress. We have 6 presentations, and we are going to start with the first one by Marta Sánchez-Sánchez from the Universidad de Cádiz.
Okay, you can see the slides? Can you see the slides?
Yes, sigue, sí. Yes.
Okay. Well, I'm Marta from the University of Granada, and today I'm going to talk about a robust Bayesian analysis in multivariated case with application in premium principles. Well, I think that it's necessary to give you a brief explanation about the Bayesian decision problem and how to apply it in risk theory. Then I'm going to give you the main result related to how to study the robustness by using in a multivariated case. And finally, I want to give you some applications related to premium principles. Well, first of all, talking about the Bayesian decision problem, we have to start with an observation. And that observation is a random variable, so it depends on a parameter. The idea of the Bayesian point of view is to consider that parameter as a random variable also. So we need to define a prior distribution, which is going to be called the prior knowledge for that parameter. The idea is to obtain what happened in the posterior case by outdoubting that prior knowledge with a sample. So the idea is to use the Bayes theorem in order to obtain that posterior distribution just by mixing the prior knowledge with the sample information. Well, if we want to focus on insurance risk, we are going to consider that observation is an insurance risk, and obviously it depends on a parameter. The idea is to consider that parameter as the random variable, so we need to give this a prior knowledge. Then we can use a sample of past information about that insure in order to obtain the posterior distribution. If we want to focus on premiums, we need to define which is a premium principle. Well, given a risk, that premium principle is a function that maps x to a real positive number, which is going to be the premium. But if we see that premium principle, it inherits the dependency from the parameter. So we can define that risk premium depending on it. If we consider that parameter a random variable, we can introduce in that risk premium the prior knowledge. And using that, we can obtain the collective premium. Also, if we have a sample and we obtain the posterior distribution, we can obtain the Bayesian premium. Well, but there is a big criticism related to the Bayesian problem, and it is related with the selection of the prior, because sometimes it is selected with subjectivity, so it's necessary to study the robustness of that selection. Why we select that prior, that unique prior? The idea to solve that is to use a class of a prior distribution in order to study that robustness. And here we have some classical examples of classes of priors. So at the end, the idea is to have a class of prior which imply a class of posterior distribution. And then that class of posterior distribution imply a set of quantity of interest, in our case, the premiums. And the idea is to study the range of that set. And if we have not so big difference, we can conclude that the problem is robust. In general, as you can imagine, it's not something easy in practice. So the idea of that work is to show a new class which allows us to make all that computation in an easy way. And for that, we need to define 3 main tools. The first one is the stochastic order, particularly the multivariated likelihood ratio order. Then we are going to talk about multivariated total positive function, and finally, the weight function. Well, here we have the definition of the multivariated likelihood ratio order. It's a way to order a random vector, so we can say that they are ordered with this if it verifies that inequation. But the interesting thing in that case is that if we have that the vectors are ordered in the likelihood ratio of also the expect value are ordered, and they are ordered in the stochastic order, which is going to be useful at the end. Then we have to define the MTP2 functions. Well, we have it when it verifies that in equation also. Particularly if we want to see in a random vector, we can say that its density function is MTP2. As you can imagine, it's not something easy to prove, and there are a lot of results related to MTP2 function, but we are going to focus in that characterization, which is an easy way to obtain if a function is MTP2, just by calculating the second derivative of the logarithm of the function. And if we see that it is bigger or equal than 1, we can say that the function is MTP2. And finally, as I said, I want to show you what is a weight function. At the end, if we have a random vector and with this prior knowledge, we can define a new density of probability, which is going to be related to a non-negative weight function, and it's going to have that expression. And the interesting thing is that that new density function is related to another parameter, which is the weighted random variable. And the most interesting thing for us is that we can use it in order to introduce uncertainty, make a little perturbation in a prior, in order to make that difference that we want in order to create that class of priors. Well, the first main result that I want to show you is the relationship between the prior distribution belief and its weight version. If we have a prior belief, which is MTP2 in the variables, and we have a weight function which is increasing or decreasing, it's easy to prove that they are ordered in the likelihood ratio order. And using that, we can define that new class of prior distribution, which is going to be called the weighted band. And it is obtained just by using two weight functions, one decreasing and the other one increasing. And the interesting thing of that class is that it's a particular neighborhood band, and we can control the whole class because we know the upper bound and the lower bound. They are achieved in the two weighted distribution. So we can control the whole class, and we can control the uncertainty that we want to introduce. So it makes all the study of the robustness in an easy way. Well, finally, the final result related to that is what happened in the posterior case. And well, if we have the characteristic that I showed in the previous slides, and we have an observed data where its likelihood function is MTP2 in the parameter in that case, we can see that the order in the likelihood ratio order is inherent in the posterior case. So at the end, the point is to find which functions are MTP2 in the parameters. Here we have some example of that, which is not something as easy to find. And if we want to show that result related to premiums, first of all, we need to consider that we are going to use any premium principle which is non-decreasing in the parameter. And knowing that, and using the class that we defined before and the weighted band that we said, we can see that the collective premium and the Bayesian premium are ordered because they inherit the order from the class. Well, knowing all of these results, I want to show you some applications, particularly where I'm going to start with a compound Poisson process model. It means we have a number of claims which follows a Poisson distribution, which a particular parameter, and then the amount of each claim follows an exponential distribution with the other parameter. We can see that these parameters are independent. We can consider them independent, and we can define the vector of prior just by defining the marginal ones. The marginal for the first one as exponential, and the second one as inverse gamma. Then if we introduce the sample information, we can obtain also the posterior distribution, which are going to be independent also. And they are going to follow a gamma distribution in the first case and an inverse gamma in the second case. Well, knowing that, that part, we are going to focus in a particular example. We are going to use as example a particular portfolio where we have one expected number of claims per client and period, and we have an expected amount per claim of 2,000 euros. Also, we are going to use the net premium in all cases in order to make all the computation easier. And also we are going to use a weight, these two weight functions, which one is increasing and the other one is decreasing, depending on the selection of the parameters. And here we also have the, at the end, the both parameters are independent. And finally, we are going to simulate different scenarios, changing the number of periods and changing the sample, because we are going to consider a sample with 3 different clients, which has different average of claims and average of the amount in each period. So at the end, we obtain that results using all the information that I showed you before. Here we have the collective premium and also the Bayesian premium in each case of client and in each period. And the first thing that we can see that they are ordered as it's supposed to be. And if we study that ranges, we can see that the difference is not so big. So we can consider that the problem is robust at the end. And the other application is a little bit something different, because it's going to be applied in a bonus-malus system. Well, first of all, I need to define which is a bonus-malus premium, which is just the ratio between the Bayesian premium and the collective premium. And it's easy to see that we are going to consider a bonus or malus client depending on if that ratio is bigger or smaller than 1. It means when we introduce the sample, introduce the information about the client, we can see the change between the collective one and the introduction of that particular client to decide if the client is bonus or malus. And if we obtain that it is equal to 1, just we say that that client is doesn't add any information from the collective one. And well, by using that, I want to use the client that I showed before. And also we need to define that family of prior distribution. All of that prior distribution belong to the class that we define as the weighted band because of the expression that it has. It is just a linear mixture between the upper bound and the lower bound. And it allows us to decide what kind of uncertainty that we want to introduce depending on the epsilon. And if we use it in order to obtain the bonus-malus premium, we have that expression. And the idea is to show how a client can change from bonus to malus or not, depending on its experience and depending on the epsilon parameter. Here we have some examples. We have the 3 previous clients and the 3 previous periods. But here we can see that some clients are always bonus or always malus, depending on the client. But sometimes we can see that a client could change from bonus to malus, depending on how is the uncertainty that you want to introduce. If you want to be closer to the upper bound or to the lower bound. And maybe it could be useful if you want to decide about a client just by knowing information of a short period of time. And well, that's all. Thank you for your attention. And if you have any question or you want to make any comment, we can talk about it in Spanish or in English, whatever you want.
Okay. Thank you very much. Marta, can you listen to us?
Yeah, now
it works. Okay, so it's time for questions. Okay, so thank you very much again.
Thank you.
Okay, so we continue with the next presentation by Badescu from the University of Toronto.
Thank you. Okay, thanks. It's as I said, it's great to be here. I've been in the summer for vacation in Barcelona, and I'm again after 2 months, so it's always a pleasure. So today I'm going to talk about a class of distributions that are equipped with regression. We call the Logit-reduced mixture of experts models. And there are some applications that we were looking over the last 2-3 years in premium, so in rate making or in estimating the IBNR. So today I'm going to look on a few applications on IBNR. And what I will be doing, I'll be proposing an extremely simple approximation for the IBNR, which is the incurred but not reported reserve, that can be used in practice as an alternative to those macro level reserving models that are currently used by practice. And this is joint work with my colleague Sheldon Lin and our past PhD student Samson and our current PhD student Spark. And it's based on different papers. So the first 2 slides, I want to just give you a very brief introduction to this class of mixture of experts and our proposed Logit-weighted reduced mixture of expert class. And I'll try to justify why we're using this class, and I'll try to justify the usefulness of this class, the properties that this class possesses that makes it extremely useful. So in general, if you try to look at the multivariate response, here denoted by Y, can be loss amounts in various lines of business or number of claims. We're interested, like the mixture of experts technically model the density of such a multivariate response as a mixture where you have the gating function, so you have some probabilities. You can view these like some latent states that depends on the covariates of each individual. So you have some probabilities denoted by pi j. Here they're equipped with regression, so they depend on covariates. And given that you're in a certain latent state, like a certain risk class, you're going to have a potential multivariate density that has some parameters that are also depending on the covariates. So this is the very general class of mixture of experts that is used a lot, not only in statistics, but also in machine learning and so on. The class is very flexible. It possesses a lot of properties, but you have a lot of parameters that you have to estimate if you're using this class. So our idea was, can we actually simplify this class without making any, without losing any generality? So what we propose to do, we propose from the density component, which is called the expert function, we propose to eliminate the regression. So all the densities are going to be parametric families that will depend on certain parameters. And we propose to keep the regression only on the weights. And in addition to that, we fix the regression model to be a Logit linear regression model given by this. So technically, this is a much simplified model. Again, we're going to leave the densities not in a regression fashion, and the regression is considered only on the weights. Now, this class of distributions, we showed in a few papers that this class of distribution, despite the simplification from the original mixture of expert class, this class of distribution possesses extremely nice properties. One that motivates the use of this class of distribution to fit any sort of data set is the denseness property. This class that is equipped with regression is dense in any class of distribution that are also equipped with regression. You can catch any sort of non-linear relationship between the response and the covariate. It's also dense in the class of mixture of expert models, so one can use this much simpler class of mixture of experts without any problem. It has nice marginalization properties, closed form solution for moments. They can be obtained in very nice solutions. Another interesting and very useful property is the identifiability property, and also that makes it interpretable. Like each of the latent class will have different risk interpretations, so you can interpret the different policy holders that belong to various classes by looking at them as having different risk characteristics. We developed certain, an EM algorithm for fitting the parameters, for calibrating the model, and the algorithm is computational tractable. So this class of distribution has a lot of nice properties and fits any type of data, at least theoretically, because we proved the denseness property. So what we did, we tried to model in various papers. We use this class for rate making, and today I'm going to show you how we use it for modeling the reserve, so looking at the IBNR reserve. Let me just start with the example. So we are using a real data set example from an European automobile insurance that has 11 years. And we break the period. In the first 6 years is the in-sample, the observation period that we're going to use to calibrate our model. And then we have 5 years that are going to be used as out-sample, the verification period. We have about 600,000 MTPL insurance contracts for which we have various covariates with respect to the age of the car, the engine, and so on. I don't have a lot of time to go over. We have about 12, 14 covariates that we are using in this. And over these 11 years, we have approximately 29,000 of reported claims for which we have the accident date, the reporting date, then the severity. Now, this is the evolution of the portfolio in this MTPL line of business. You see that the business increased in time until year 2017, and then there was a drop, significant drop. Probably the insurance company eliminated various very risky policy holders. And here on the right-hand side, I have the number of claims, so the claim intensity per exposure. And as you can see, there is a downward trend. However, we did some analysis, and this trend, this arrival rate, doesn't really depend on time, but follows a downward trend, actually due to the fact that some very risky policyholders are eliminated from the portfolio. Now, when you try to look at the modeling of the incurred but not reported reserve, there are two big type of models that are used: the macro level models that are aggregate, and the micro level models, which are very there's a lot of literature lately on these models that consider a lot of information that is not actually considered in the macro level models, which are Chain, Letter, Bourne, Hutter, Ferguson, and so on. So we're trying to imply some sort of micro level model, and we have 3 papers about modeling the IBNR, and in the beginning I'm going to assume a very simple Poisson assumption. So we're going to make the assumption that the number of accidents is going to be Poisson. So the number of arrivals is going to be Poisson. And if one writes the likelihood of such a process that has the arrival process, and then after the arrival there is a reported delay, right? The claim is reported after a random horizon, and then when the claim is reported, you have a development that contains information about the payments, about the changes in case reserves, and so on. One can, if you want to write the likelihood, one can express the likelihood as a product in general, as a product of 3 terms. The first term depends on it's a likelihood that depends on the number of reported claims. The second term, G2, contains the likelihood that involves the reporting delays, and the last term contains the likelihood, let's say for simplicity, that involves the claim sizes, right? Now, the usual way of dealing with the maximization of this, first, it cannot be done together because it's very complicated. What people are doing in the literature, they start with the reporting likelihood. So U here denotes the reporting delay between the accident and so the time between the accident and the time when the claim is reported. And then once we make some assumption on the reporting delay and we obtain the parameters, then we plug it into the likelihood that corresponds to the number of reporting delays, and you actually estimate the lambda. In this case, we're going to use a Poisson GLM. And then we can separately also estimate the claim sizes, and then we can put them together and estimate the incurred but not reported reserve. Now, the The biggest challenge here is that this likelihood in the denominator, it has the probability that the claim is going to be reported prior to this quantity. Tau is the valuation time, and tk represents the accident time. So you have a likelihood that corresponds to a truncation. It's a truncated likelihood, right? And the problem here is that all these points are changed, right? Depending where an accident occurs, each of these reporting delays will be randomly truncated. So to estimate this type of likelihood is not trivial at all, actually. And in the first paper, what we try to do, we completely ignore, as an example, we completely ignore the denominator. So we just fit the untruncated likelihood. And the results when we predicted the IBNR were still good. However, obviously they will be biased, and because they will underestimate because we're not considering the denominator, the IBNR will be underestimated. Another way to deal with this, and that's what we did in the second paper, in the case study in the second paper, we actually, instead of looking and fitting the reporting delays for the 6 years of in-sample period, we choose a 5-year period, so a smaller period, and we observed that almost 99% of the claims will actually be settled in the last year. So in fact, this denominator will converge to 1, and therefore we still use a density that is not truncated. Obviously, when you are going to get better results in terms of bias, but you're going to have bigger variances because you're going to use less information, right? And just to show you this second type of analysis, what we did, we fit this class of LR, Logit-weighted reduced mixture of experts for the reporting delays. We also fit the same thing for the claim sizes. We fit a Poisson GLM, and then we have the distribution. We use Bootstrap to obtain the whole distribution of the incurred but not reported reserve. And here, the red line is the point, technically, that is observed from the out-of-sample data, the 5 years that we observed that we left aside, that most of the claims are settling in that period. And the difference is, well, you see that the IBNR is very well predicted by our method. However, if one ignores the covariates from the analysis, the IBNR is badly underestimated, right? The true value, the red value is badly underestimated if in the model covariates are not taken into consideration. So this is one initial, well, let's say a simple analysis. The next question that we were asking ourselves was how can we actually deal with this part? Can we actually derive some sort of fitting algorithm that is going to accommodate for random truncations for the reporting delays? And what we did, yes, we were able to do so. Normally, if you have the same truncation point, is not very complicated to derive an expectation maximization algorithm, but when you have a random truncation point, the problem is that you're going to reweight this mixture, and the new weights are going to be different, and they will depend on covariates, so you cannot use the same type of EM algorithm. Therefore, what we did, and I'm not going to go into details, we constructed, as the EM algorithm works, we constructed a set of complete data. So we took each observation, which in our case are the reporting delays that we observed prior to the valuation point, and these are contained here in this vector y. And for each of it, we hypothetically generate a number of geometrically distributed reporting delays that will occur after the valuation point in time. And K, this vector, contains technically how many hypothetical claims of that type I will have reported after the valuation time. Then this vector contains all their reporting values, and then we have some other vectors that are going to account for which expert class in the mixture of expert each observation is going to belong to. Anyway, the key point here, and again, obviously, the number of reported delays are not going to be geometrically distributed, but in the EM algorithm, this parametric assumption does not affect at all our calculation. The fact that we have this geometric probability mass function helps us to simplify a lot the likelihood and helps us to obtain a likelihood that can be calculated numerically in an easy way. Now, let's come back to the IBNR estimation, and I'm going to focus now only on the number of incurred but not reported claims rather than focusing on their sizes as well. If one assumes that the number of accidents follows the Poisson distribution with a not necessarily a homogeneous process, not necessarily a homogeneous Poisson process, it is very easy to show that if you have a reporting delay, technically the number of reported claims prior to the valuation time will also be Poisson with shifted intensity that contains the CDF of the reporting delay, as well as the number of incurred but not reporting delays is also Poisson due to the thinning property of the Poisson, and here you have the survival probability of the reporting delays. Now, normally what we have to do if we are doing our analysis, I'm going to first fit this reporting delay, then I'm going to put a GLM on lambda to find the intensity of the Poisson process, and if I want to find the total IBNR, I have to fit the claims. However, what we're able to show under this particular case is that if you take this K and then you actually add all these parameters that are the realization of your simulated data points in the expectation maximization process, in the calibration process that we propose. So technically, if you take for all the reporting delays, right, U is the reporting delay random variable. If you take the survival probability that the reporting delay is going to occur after the valuation point, this is WI represents the highest accident time, and then you divide it by its CDF, so this is technically the mean of the geometric distribution. This is an unbiased estimator for the intensity of the IBNR for this lambda, right? So then I don't need even to calibrate my number of accident process. The only thing that I need to estimate the number of IBNRs is this statistic here that is an unbiased estimator for lambda. Now, because the LRMOE, the mixture of expert class, is it's dense in any class of distribution equipped with any regression, then our proposed model is obviously to approximate this reporting delay distribution using the LRMOE class. So that's what we're going to do, and therefore we're going to get an unbiased estimator for lambda. And here, the last two slides coming back to the numerical example, we have separated the out-of-sample period. First is 5 years, then in the second run we use less 4 years, 3, 2, and so on until 1 year. And here is the total IBNR that we are going to obtain, the mean of that Poisson process. Obviously, because the out-of-sample period is going to be shrinked more and more, we have to calculate some sort of that we call a truncated IBNR, given the fact that we observe it for 5 years, for 4 years, for 3 years, and so on. And this is actually the realized value. And then, well, all our values are in the 95% confidence interval, and they are not very different than the realized values, despite the fact that we just fit the reporting delay to estimate the IBNR. And finally, we did a comparison with the classical chain ladder method, which is the one that most of the insurance companies are using. And here is the exact value. These are all truncated values. This is the red value, is the exact value. This is the distribution of the IBNR using, again, Bootstrap. The green one is the chain ladder, and the blue one is ours. And as you can see, ours I would say, I don't know, 2 or 3 out of these 6 cases is better than the chain ladder. Chain ladder always underestimates the real value of the IBNR. And here in the last example, so when we have in this run where we don't have any out-of-sample period to compare the estimator, if you look here, the total IBNR is going to be dropped significantly. If you look back to the exposure of the data, there is a huge decrease in the exposure in year 2017. The chain ladder cannot capture that sudden change in the portfolio. You have only 1 year that is observed in that particular case. So the chain letter estimation, it's way bigger compared to our estimation. So the chain letter is not able to capture this type of drastic changes in the portfolio or drastic changes in the risk associated with the policyholders. Yeah. To conclude, well, what we are working on, we are actually able to extend this type of analysis and to show the same unbiasedness property if you move away from the Poisson process assumption that represents the number of accidents and assume a more general Cox-type process where you may have a stochastic intensity that depends on the covariates. Another thing that we're doing, and we actually just submitted a paper last week, we added to this mixture of expert class random effects that are going to make the model more general, and you can use some sort of posterior analysis for rate making and posterior classification that is much better. As you can see in the paper, I will have a reference to the archive where we put it down. We applied for rate making, and technically we can keep track using these random effects. We can keep track on the unobservable risk associated with each policyholder. And well, eventually that's a long-term problem that we'll be looking to bridge these stochastic claim reserving to the premium, the rate making problem under certain micro-level models. Yeah. So here, there are some papers that we published in the last few years, and 2 points here. This is a paper that contains all the codes, there are codes and codes that are written in Julia. I haven't had the time to talk about the experts. One has to decide on what sort of experts one uses for the density, for the expert densities. And there are a lot of different parametric distributions that are actually implemented in both R and Julia that the user can choose from. There are a lot of, like there is a manual where you learn how to fit continuous or discrete distributions in a uni or multivariate context. And this is the last paper that we just submitted. It's on archive. You can find it. There is also another paper that Samson and 2 other PhD students, it's a theoretical paper that proves that the new class with random effects is also dense and possesses also very nice properties. So I'll stop here. Thanks.
Okay, thank you very much for your talk. We have time for fast question. Just one question. No?
Yeah.
In your EM, if I'm not taken wrongly, you assume this geometric distribution there, but actually this is an intermediate assumption just in order to be able to go with your EM. Is it correct?
Yes.
But I think that typically when you describe an EM, this is one assumption that it is underlying the model. It is not, let's say, so actually if you change this assumption, have you seen if the results will change? I understand that this is done for convenience, but
it's
actually
done for
this can drive a little your results. Have you tested something different?
Yeah, it's not effective. Like you have an incomplete data and then you make a complete data assumption. So you construct the likelihood. So there's absolutely no cost that we're paying.
If I change this assumption,
then we will not be able to apply it for this type of truncation algorithm because the likelihood will not be changed in a nice form. So you cannot maximize that expectation. Okay. So this assumption is completely, you can make any, like you can assume that they are negative binomial or whatever, right? But if you plug that into the likelihood, you're not going to get a nice likelihood.
Yes, yeah. Exactly that. Yeah. But actually your assumption, I mean, if you could have a nice formula, you get a slightly different results. That's a concern. If this assumption
if you have, exactly, okay,
thanks.
Okay, thank you very much. We thank the speaker for the presentation. Okay, we continue with the next speaker, Juan Yanez from the Université de Québec à Montréal.
Okay, greetings. My name is Juan Sebastián Yanez. I'm a PhD student at UQAM University, and this is a project that I've been working on with Professor Mathieu Pigeon and Jean-Philippe Boucher. The presentation is going to be divided in two parts. First, we're going to talk about the model that I'll be presenting today, and then we're going to look at some numerical results for that model. So this is a dynamic claim score modeling. I'll explain what score modeling is in the context of the paper. So to begin, I'd like to just establish a little bit of a timeline. So as you know, whenever a claim occurs, there are a series of events that are going to happen. So there is the occurrence of the claim itself, then the reporting of the claim. Eventually, there are going to be some cash flows, and the claim is going to be closed. So the idea is that within the reporting date and the closure of the claim, there's going to be this window of time where payments are going to occur. The idea is that we see this timeline as a period of time, which is going to be between 0 and tau I, which is going to censor or close basically the claim. And within this period, we're going to do a division. So this division is based on time intervals that can be chosen in different ways. I guess the easiest way would be simply to define them as a yearly division. We can also choose a monthly division, depends on how the claims are behaving or simply how the actuary wants to divide it. So if we look at this idea in a figure, you can see here two claims. One is RBNS and the other is IBNR. And in this presentation, you can see a dotted line. This one is going to represent the reporting delay, so the delay between the occurrence and the reporting of the claim. And then we have a solid line, which is going to represent the window that is of interest, so between the reporting of the claim and the closure of the claim. Of course, we have to have a valuation date. So after the valuation date, we find the values that we want to predict. And as you can see, we have the same idea that I talked about earlier. So we can see that there is our period of observation with the solid line. And within that solid line, we do the division based on a vector that contains the different divisions that we chose for the portfolio. So if we look at claim 1, for example, the issue is that some of the observations are going to be censored simply because we end up in the valuation date, and sometimes the intervals may be divided by simply by the censoring date. Other than that, we can then establish the values that are of interest, which are the number of payments. So these are described by dots in the graphic I showed earlier. And we're going to establish a vector in I, which is going to contain all the number of payments for each period of time, depending on the vector that contained the time divisions. So, of course, another value that is of interest is the exposure associated to each of these intervals. The idea is that whenever the claim is closed, there is no payments can occur simply because the claim is closed. Another interesting thing about the exposure measure is that, of course, if we end up in a censored interval, this value is going to be inferior than the usual value. So this is an exposure that is going to be associated to each interval. So we end up basically with two vectors, NI and EI, which is going to contain number of payments and the exposure for each interval. That is. Then we're going also to add some information to help us do the prediction. So this is very classical. The idea is to include different types of covariates. Since we're in a micro level setting, we can use all the information that is available regarding that particular claim. So this can come in the form of a static covariate. So these are, for example, covariates that do not change over time, such as the region where the accident occurred. We know it at the reporting date, and then, of course, it's not going to change as the claim develops. There are other types of covariates that can be used that are called dynamic covariates. So these are covariates that do change as time progresses. However, they are not random. For example, the age of the person that was injured. If the person was injured at 25, let's say, then 2 years later, we know that person is going to be 27 years old. So the variable does change over time. However, the value is known. Now, this gives us a very classical framework where we want to calculate, to predict basically the number of payments. So we can establish the mean parameter, mu ik, which is the expected value of the number of payments given all the information that we established earlier. So that is the covariate vector, the covariate values, and the exposure. So we end up with that. Again, very classical. We have the exposure multiplied by the inverse of the link function, and the link function is fed with the information that is available. Now, for our paper, we decided to include information that does change over time. Basically, we wanted to use some information that evolves in a random manner, but can improve the predictions, or so we hoped. So the idea is that we calculated 3 measures that are going to be combined into a single value. I'm going to describe those measures. So first we have epsilon ik, which is the cumulative exposure. So we're going to see how long a claim has been open up to a given interval, say, for example, dk. And then we're also going to count the number of payments that have been observed up to a given interval. That's eta ik. We're also adding a third measure, kappa ik, which is going to count the number of, which is going to count the exposure of payment-free periods. So whenever a period does not have payments, we're going to add that into a value that is going to be added, that is going to grow eventually. Now, with these 3 elements, we can look at the same structure we had before. We have the mean parameter, which is, again, exposure multiplied by the inverse of the link function. However, this time we are including all 3 elements into our function. We have, first, we have minus kappa ik. So we have a minus because this value usually affects negatively the value of the mean parameter, simply because if we have more periods without payments, this is going to reduce the value of the mean. Then we also have another value, which is basically the previously observed frequency, so the number of payments divided by the exposure. Then if we factor in all the values into a single parameter, we end up with what we called in the paper a claim score. The claim score is equal to minus kappa ik plus C multiplied by the previously observed frequency. So C is called in the paper a jump parameter. And of course, we have gamma as the parameter that is multiplied to our claim score. So for people that have studied bonus-malus models, this is inspired from those models, actually. So this is very similar to a bonus-malus structure. The idea is to have a risk measure that evolves over time. So whenever we go from one interval to another, we end up with an updated claim score. And this hopefully is going to feed information into our model that is going to improve the prediction. So as the claim evolves, we get more information, and this is going to affect future predictions. Now, for a more practical problem, since this approach is used mostly in price making models, we had to adapt the structure a little bit. So especially because in a micro level setting, when you count the number of payments, you can end up with a lot of payments that can occur at once, for example, for a given interval. This, of course, gives information that is important, that may indicate that the claim is more risky, so it's more prone to produce payments. However, if too many payments occur, this is going to affect greatly the value of our claim score, and this could overestimate the number of future payments. So by analyzing the data, we realized that adding a cap to the claim score improved greatly the results. So basically, this is what we ended up with. So the same idea, we have the claim score that I showed earlier, but we're going to include a cap Lmax. So we're going to choose between the minimal, between the value that we calculate with the formula, and a maximal value. This gives us basically a 3-parameter structure where we have the gamma parameter, then we have the jump parameter, and of course, the maximal value. Now, this is the basic idea of the paper. There are other nuances, but with this short presentation, I'm just showing you the basic idea. And Then we're going to look at some numerical results to see how efficient this structure was when we fitted different models using this measure. So regarding the data set, we used a data set with 57,000 AB coverages, and the analysis was done between 2011 and 2017, and we chose 2015 as our valuation date. So this gives us 2 years of observable values that we can compare with the predictions that we're going to make. So just as a general information, the portfolio contained around 49,000 closed claims, 8,000 open claims, and around 900 unreported claims. Now, to add more depth to our analysis, we also included a division in terms of payments. So we looked at the nature of each of the payments that was done in the data set, and we decided to divide it into 3 categories. First, we have medical payments. So these are payments that are related to anything regarding medical treatments, so cost of exams or any other medical bill, basically. Then we divided also the payments into the disability category, which is going to be a more recurrent type of payment that is going to be based on the disability income and the caregiver disability income. Again, more of a recurrent type of payment. Then we also chose an expense category, which is going to include all the other expenses that are not medical or disability. Now, when we fit classical models, we can make a comparison whenever the claim score is included and whenever it's not included. So in this table, you can see that we fitted 2 classical models, the negative binomial and the Poisson. For each of the 3 types of payments, so we have medical, disability expenses, again, medical disability expenses for each of the models. Then we can use the AIC to compare the models. So we have in the first column, we have the models that include the claim score, and then we have the models that do not include the claim score. So again, we can see that all the values are inferior. So according to these criteria, it seems that the model is improved when a claim score is included. Then we can also do another classical test, the student t-test, and we're going to test whether the gamma parameter, which is the one that is multiplied to the claim score, is relevant or not. So we can see that the p-value is very low with very high t-values. So again, indicating that it seems that the claim score is relevant in terms of predictability. Finally, we can do a simulation analysis. Same idea, we have models that include the claim score and models that do not. This time we're going to use the cumulative value between all 3 types of payments into a single value, and we can do a comparison. So here we have the mean, the standard deviation, and the values at risk, 95 and 99%. And the final column is going to contain the observed value. As you can see, whenever the claim score is not included, the model is not that efficient. The mean is and the values at risks are lower than the observed value. Even the 99% value at risk is lower than the observed value. However, when the claim score is included, it improves the model a lot. Basically, we have all the values at risk are higher than the observed value, and the mean seems to be closer to the observed value as well. So a general upgrade in this simulation comparison. With that, I'm going to finish the presentation to have a little bit of time for questions. So here you have some of the references. So the first we have the paper that is from which this presentation was based, and the 2 papers that inspired this work. So another paper that I worked on for my PhD thesis, which is based on the micro level models, and the bonus-malus model that also helped us write this paper, which is by Jean-Philippe Boucher in 2021. Thank you very much.
Okay, thank you very much for your talk. It's time for questions. Okay, we thank again. Thank you very much. We continue with the next talk by Enrique Calderín-Ojeda from the University of Melbourne.
Hello, everyone. Thank you for having me here online, virtually, in this risk conference. Unfortunately, some health problems just prevent me to attend in person to Barcelona. Okay, so the paper I'm going to present today is just a joint paper with Professor Gómez-Déniz from University of Las Palmas, Spain. And the presentation is entitled Introducing a Nonlinear Regression Model in Excess of Loss Reinsurance Content. Okay, so the idea of this paper is very simple. Okay, so we are going to work basically with excess of loss reinsurance, a local type of reinsurance arrangement, and from the reinsurer perspective. Okay, we're going to introduce a model, a parametric model for the distribution of the claim payment for the reinsurer, and then incorporate some inflation in the model. Okay, so this is just the presentation, I mean the outline of this presentation, of this talk. So we're going to introduce our methodology in the first slide, and then just give a setup or a background of the excess of loss reinsurance and the methodology we are presenting today. Okay, then we move to the specific results. So just for a better understanding of this methodology, we are going to give a specific model. In particular, we're going to work with a particular case of the gamma distribution, and then derive the parametric model of the distribution, the density function of the claims paid by the reinsurer. Okay, the expression is more or less simple, and then we're going to reparametricize the model in order to include some covariates. Okay, and then well, under this transformation, which is non-linear, we're going to incorporate these specific covariates and also the inflation rate in the model. Okay, then we have some numerical illustrations based on a very well-known data set in the actuarial literature. And finally, just give some summary of the presentation. Okay, then in the presentation, we're going to work with the excess of loss reinsurance. Okay, just a local type of reinsurance, in particular focusing on the reinsurer position. Okay, in the reinsurer position. Just to refresh, under excess of loss reinsurance, under this arrangement, the claimant, the individual payment, is shared between the insurer and the reinsurer only if the claims exceed a certain quantity. This quantity is known as the excess or the retention level. Okay, then we're going to introduce a parametric model just to calculate the excess of loss distribution from the reinsurer perspective, and then just examine how we can incorporate covariates in the model and how this covariate may affect the expected payment. Okay, then in the application, so we use the data from a real motor vehicle insurance portfolio, and we're going to consider both indicators and continuous explanatory variables. Okay, we're going to see in this very simple model that the numerical results suggest that the choice of the retention level and affects especially the significant level of some of these explanatory variables. Okay, and in particular also not only the retention level but also the inflation rate that we introduce. Okay, and finally, as claim size often increases over time due to inflation, we examine how this can affect the reinsurer payment. Okay. So then start with the background, just the definition here of excess of loss reinsurance. So let X be a random variable denoting the size of a claim. So a reinsurance arrangement is an agreement between an insurer and a reinsurer under which claims that occur in a fixed period of time, say for example a year, are split between the insurer and the reinsurer in an agreed manner. Okay, so then the insurer insures part of the risk with a reinsurer by paying as compensation a premium to the reinsurer for this cover. So then the goal is just the reinsurance agreement reduce the variability of claim payments by the insurer. Okay, in particular under excess of loss reinsurance, by fixing the mean of the distribution, then the variability, the variance is reduced among all the local type of reinsurance. Okay, then the random variable X, representing here the amount of the claim, is split into two quantities, Y and Z. So X is equal Y plus Z. Where Y is here, the random variable denoted the amount paid by the insurer, and Z is a random variable representing the seed amount to the reinsurer. Okay, so then under this excess of loss reinsurance, the loss is shared between the insurer and the reinsurer if the amount of the expense exceeds a fixed quantity, so the retention level, say Q, and this Q is assumed to be greater than 0. Okay. Otherwise, if this is not the case, so then the insurer assumes the whole loss. Okay, then mathematically speaking, so we have that the random variable Y, that is the amount retained by the insurer, is just defined in terms of the distribution here of the minimum of X and Q, where Q is the retention level. So the random variable X, I didn't mention that before, but it's assumed to be a non-negative random variable, okay, in our methodology. And then the seed amount to the reinsurer is just denoted by the maximum of 0 and X less Q. So then we can easily derive the moments of the random variable set by using this well-known formula. Okay, just integrating alongside the X, the maximum of 0 and X minus Q to the maximum of M multiplied by the density function of the claim size. Okay, so this is integrating from Q to infinity, this X minus Q to the power of N, and from this taking just N equal 1, so we have just the moment, the expectation of the seed amount to the reinsurer. Okay, then we can write, assuming that the distribution of Z is conditional to be non-negative, the density function of the random variable Z, okay, can be rewritten in terms of the density function of the random variable X. In particular, the density function of Z is the density of X evaluated at Z plus Q, at this particular Z, divided by the survival function of the random variable X at Q. Okay, and of course, with inflation, the reinsurer's payment with the retention level Q fixed will be increased, okay, especially under this here excess of loss reinsurance. Then we are going to give just our parametric model in this slide. So assuming that the tau, the inflation here parameter is rate is greater than or equal to 1, okay, we have that we can split into two distributions, and we're going to focus on the distribution from the reinsurer's perspective. Okay, so we have the Y star here that we don't take this into consideration, and we focus on the seed amount to the reinsurer if we are considering inflation. Okay, so then the new random variable takes the value 0 when X is less than or equal to Q, and tau X minus Q when X is greater than Q. Okay, it is simple to see that under the transformation of random variables, so we can find the density function of the random variable Z star, okay, the seed amount to the reinsurance after here considering inflation, and we can rewrite the density function in terms of the density function of X, so evaluated at this star plus Q divided by tau, okay, and then divided by tau multiplied by the survival function of for the distribution X of Q over tau. Okay, obviously for the case tau equal 1, so we were in the situation where no inflation were assumed. Okay, and then we are going to introduce the specific model. So for the specific model, just for the sake of simplicity, so we are going to assume a gamma distribution with taking just the shape parameter equal to 2 and rate parameter equal lambda, okay, greater than 0. So now it is well known that the density function of this distribution when lambda is greater than 0 and assuming x to be positive is given by this expression. Okay, lambda square x exponential to the negative lambda x. So then, assuming inflation, so we have that for this particular model, because it is simple to derive an expression for the survival function. So we have that the density associated to the seed amount for the random variable z star is given by this expression here. Okay, so we have lambda square, we have the exponential term, the z plus q, and divided by tau, multiply tau plus lambda q, and assuming that under the transformation, this number is greater than 0. Then the mean can be calculated, and for this parametrization, the expectation of the seed amount is given by this expression here. Okay, just and from this expectation labeled here under number 2, expression number 2. So we have that this expectation just decreases with the retention level and also with lambda. Okay, just the derivative of this expression with respect to q and lambda is negative. But on the other hand, differentiating with respect to tau, so this is increasing, I mean, the expectation of z star. So this derivative is greater than 0. Okay, so then in order to include some explanatory variables in the model, so we can set this expression here, the mean equal to a certain parameter theta, okay, and then solve for lambda. Okay, and we have a closed for expression for lambda, in particular equal to tau, a certain function that depends on tau and the retention level q, and divided by 2 q tau. Okay, the form of this functional expression m here is given, it is easily solved by solving a quadratic equation, and is given by this expression that is highlighted on the slide. Okay, and we have this. So then, of course, forcing that the mean has to be positive, the mean of the z star, theta greater than 0. So for that reason, we can assume a long link function, okay, because we have that the mean here of the variable z star is obviously positive. So then we assume a log link function, and then by selecting a particular sample in practice, so we have that the parameter theta is equal to the exponential of the transpose or the vector of the explanatory variables of covariate, represented here by this eta, and multiplied by the column vector of the regression. In general, we're assuming p covariates, okay, and one of them is considered to be the intercept. Okay, and as an application here, we are going to consider the dataset given, is very well known in the actuarial literature, in the book of De Jong and Heller, published in 2008, also appears in the CAS dataset as well. This is an automobile insurance portfolio that corresponds to the year 0405 and contains more than 60,000 observations. Okay, so, and in particular, approximately exactly 4,624 filed at least a claim. Okay, so this is just a positive claims amount. Also, just in this quick application, so we consider the claim amount as the response variable. Okay, and then we consider certain explanatory variables. For example, the vehicle of the value in $10,000. So the vehicle age as a categorical one, the gender as a categorical one. So the or dummy variable, the number of claims, and also the driver's age category, where the reference category here is the 6. Okay. So then in the application, we consider first the case with no inflation, and we have estimated the parameters for 2 different retention levels. Okay, in particular, Q equal 250 and Q equal 1000. And we have here just the output. Okay, so we estimate the covariates and the intercept. Note that initially we have under this retention level, 3,843 observations, and for the case that we increase the retention level, we have 2002. Okay, the significant level is given by 1, 2, and 3 star, representing here the 10%, 5%, and 1% significant level respectively. Okay, so we see that the number of significant variable, the significant variable, just well, we have estimated a standard error, and then significant level given here only when this is verified. Decreases when we increase the retention level. Okay, and the negative of the log likelihood is also shown in the bottom line of the table. And as a second application, we have now a situation, similar one, but we are incorporating some inflation rates. Okay. In particular, keep the same Q, the same retention level, and then study this under inflation 1% and 2%, okay? And same for the second situation here, retention level 1,000 and the same two different inflations, okay? Again, we have that with increasing the inflation here. Well, we have similar result for the case 250 in terms of significant parameters, okay? And well, the estimates are more or less quite similar. Note that the number of observations just increasing the inflation, so we have 3,854 here, okay, for inflation equal 2%. And for the case, the retention level equal 1,000, so the number of significant variables, covariates, are much lower here, okay? So then this is the application that we have done for this simple model, okay? And conclusions and summary of this presentation is given in this slide, where we have introduced a parametric model to calculate the excess of loss distribution from the reinsurer's point of view and examine how we can incorporate certain covariates that incorporate the payment. So the model has been applied to this very simple model, a particular case of the gamma distribution, and in the application we have seen that how the explanatory variable and the covariates just behave when we increase the retention level and the inflation rate. Okay, some reference for this work as are shown in this final slide. Okay, and this is all for the presentation.
Okay, thank you very much for your presentation. Now it's time for questions. Okay, so thank you very much.
Okay.
And now we continue with the presentation by Luis Bermúdez from the University of Barcelona.
Okay, good afternoon. Well, the presentation is about an ongoing paper jointly with Dimitris Karlis, that is also here. And it's about modeling and observed heterogeneity when we try to rate making some policyholders in a car or a automobile insurance data set. When we want to do that, when we want to model claim counts, usually we find this problem of unobserved heterogeneity. Unobserved heterogeneity is caused by the differences that in driving behavior or driving habits or among policyholders or among drivers that cannot be measured or observed by the actuary. This problem, well, this is a problem because often leads to overdispersion and or excess of zeros that cannot be handled by a Poisson regression model. As probably you know, many attempts have been made in the actuarial literature in order to account for this problem. For instance, zero-inflated and hardened models for the x's of zeros, and compound frequency models as negative binomial for the overdispersion problem. However, a natural way to deal with this unobserved heterogeneity is to consider mixtures of simpler models. And what we are, or when we are working using finite mixtures of some typical regression count models. Well, this is the expression for the usual expression for the use for the finite mixture of regressions. We have k groups. So the idea is that our portfolio, in our case, is comprised of 1, 2, 3, or 4, or up to k groups of policyholders that are defined by these unobserved factors. The question here is that the mixture is weighted by this proportion that we call mixed proportion, and it's equal for all the observations, but we have for each group one of these proportion. Well, in the rate-making literature, of course, we use J as the number of claims for the I individual, and also we have a vector of covariates with all the information of all the observed information of this individual. If we assume a finite mixture of Poisson or negative binomial, as we did in a previous paper in 2020, these allow us to take into account overdispersion and the x's of zeros at the same time. But also allows for the typical clustering in finite mixtures. So these allow us to identify different groups of drivers, as I told you before, defined by these unobserved factors. Well, in this previous paper in 2020, we applied this approach to a portfolio, and this is the four conclusions, the main four conclusions. The first one is that these finite mixture regression models, Poisson and negative binomial, produce best or better fits than the classical models. I mean GLM and zero-inflated models. We also see that the portfolio consists of two groups of policyholders that we call good drivers and bad drivers. What it was more interesting is that these two groups exhibited different regression structures. This is different scores or different effects on covariates depending on the group that the observation belongs. And for the same reason, the fourth conclusion is that the two groups exhibited or they had very different expected claim frequencies. Okay, in the following slides is just only a review or some tables and figures to check these conclusions I've just mentioned now. This is the data set. We have more than 80,000 observations, and we have the number of claims reported by the policyholders, and these 7 covariates, all of them binary covariates that are the usual ones: gender, the zone, the driving zone, the power of the horsepower of the car, etc. As I told you, here you can see how the two finite mixture models give better fitted than the GLM models and the zero-inflated models. Here, what we can see is that with this two-finite mixture, with the two-finite mixture negative binomial, we have these two scores. One for the first group, the good drivers, and this is for the bad drivers. And we can see that the negative binomial with just only one score is something in between these two. It's like a weighted average of these two scores. And what is interesting, for instance, with the variable with this covariate URB, that is if the driver or if the car drives in a urban zone or not, we can see here that the effect is the opposite in one group and to the other. And how this covariate that is significant in the finite mixture, it is not in the negative binomial, because when we averaging these two, we get something close to zero, and the effect is cancelled out. Okay, here in this box plot of the fitted means, we see clearly the group separation. This is for the negative binomial model, and this is for the Poisson model. Okay, I don't know. Yes. Okay, so up to here, I show you the advantage of using the finite mixture models in terms of goodness of fit and in terms of better interpretation of the data. But some limitations, or we found some limitation when we use this model to predict a new observation, a new policyholder. So when we want to predict the premium for this new observation, this new customer, we don't know, of course, the response, and we cannot assign to one of the two groups, good or good drivers or bad drivers, and so we cannot use the corresponding score. So and so we have to use the standard finite mixture way of predicting, which is using the mixing proportions and predict with an average, a weighted average with these mixing proportions of the two scores. If we do that, if we do this weighted average of these two scores, we get something very similar to the negative binomial. So we have not better results than the negative binomial. So this is the problem, and what we are in this paper trying to give some approaches, some solution in order to take advantage of these two scores, two different scores. Okay, when we face this problem, we realize that it's not an easy problem, and and little is known in the literature about this, and there is some literature with this approach that could be to assign covariates in the mixing proportions in order to have different mixing proportions depending on the characteristics of the observation. But the problem with this is that you may destroy the model building, because which covariates you put in one part, which covariates in the other part. So to avoid this point, we propose a new extension based on an algorithm, on a classification-based algorithm. And well, this is, as I told you, an ongoing work, and this is a generic proposal that we are still working on it. Well, the first step is fit the finite mixture regression model, and then for a new observation Q, we find that, the observations that from the training data set that are closer with some distance criteria to the new observation. And looking only at the characteristics, the observed factors. And we denote this set of observation as SQ. Okay, the third step is derive new weights in order to substitute in some way the mixing proportions according to some classification criteria. We can choose for a soft classification approach by calculating some weights for each group. For instance, using the mean posterior probability for all the observations only in this group, not in all the portfolio, but just only in the closest observation to the new observation. And another possible option is use a hard classification approach that is just simply assign the new observation to the group J with higher mean posterior probability. And in this case, this new weight, it will be 1 for one group and 0 for the rest of the groups. And then when we have these weights, then we predict using as the standard finite mixture approach, a weighted mean of the scores. But now this is not equal for all the observations, and this is what we hope we improve our predictions. Okay, how can we obtain the weights? In many ways. We are still looking for the best. And as I told you, if you use the standard finite mixture approach, you just take the mixing proportion equal for all observations. If you use this soft classification, we change this mixing proportion, but a proportion that is different and is defined by the closest observations of the new observation. And the hard classification, this could be one is just take if the mean posterior is even or is largest, we have 1, and otherwise we have 0, as I told you before. But we can use other definitions. That is the point that we are still working on this. This is of course the different variants. Okay. Okay. In our case, because this is a generical proposal for any kind of data, but in our case we have a characteristic that we have 7 binary covariates. And so it's very difficult to, well, not difficult. There is no distance. I mean, the only possible way to create this set SQ is with a matching coefficient. So only observation with the same exact 7 values for the covariates are the ones that belongs to this set of observations. Of course, with continuous covariates, it will be easier because we can define, for instance, an Euclidean distance and goes much better as we test with some simulations. Okay, well, here are some results that at least help us to follow analyzing and to follow thinking in the best way to work. But if you see, this is the predictive accuracy according to this standard mean absolute prediction error, and you can see here that the finite mixture, as I told you before, is almost the same than the GLM models. We don't see any improvement, But here, with the hard classification, we improve quite a lot. And with the soft, depending on the way of defining the weights, we obtain a similar, and here well, a slight improvement. So well, we now, but even the predictive accuracy is similar to this one. We think that when we calculate premiums, we can adjust a little bit more the premiums. So of course this is an average, and in average we obtain the same predictive accuracy, but when we calculate the premiums, we can adjust more the premiums according to if the new observation is closer to the group of good ones or the bad ones. Well, the conclusions. Well, we obtain with this new extension similar or better prediction accuracy than with the GLEM and the finite mixture using only the mixing proportions. And but what we are pretty sure is that we can obtain more suitable or appropriate premiums according to this group separation. We performed some simulations with other type of data, and as I told you before, with continuous data, everything works much better than with this special case, that it was our first idea, but we realized that these binary covariates give us some problems. And well, thank you for your attention.
Thank you very much for your talk. Okay, it's time for questions.
No, this is just only experience for 1 year. This is across. We have some other works, including, but here our aim was just only with 1 year experience. Okay.
And the second question: how do you decide on the number of?
Oh, yeah, good question. Yeah, well, we use different kind of number of groups, and we see that with in this particular data set, with 3 groups, the goodness of fit doesn't improve. So we keep with 2, just only with 2.
More questions?
Yeah, I have another question. I have always wondered, and this is perhaps a naive question, but I would like to know your opinion about what you think that when you're doing this grouping of the observations, in some sense you are selecting certain factors that make your units more homogeneous inside the group and heterogeneous between the groups.
Mm-hmm.
And I wonder if some of the things that have been designed for variable selection and variable importance in this machine learning methods,
Mm-hmm.
where you just remove one of the variables and put it back again, and then you somehow have a measure of the impact it has, that perhaps that could be applicable, or maybe the way you have done this can help you decide how to split your group
Mm-hmm.
and beforehand, before trying to mix it again.
Yeah.
Because maybe you're asking too much. But I don't know.
Actually, what we have, well, we think about this significant importance of the covariates, but we were thinking in order to define these new weights, because maybe we can use the most important covariates in order, or just only to take not the information of all the covariates, but only the information of that covariates that are more important, but not before, because the finite mixture, of course you can select before, but then it's like you are putting the covariates that you are putting aside, is like you consider as an observed factor, and so it's like you have the finite mixture has to work more, because you know it's like you want balancing, or what we try here is that okay, you have some observed factors, okay, and what about the unobserved? So the only, I don't know, and maybe with the telematics we can avoid this finite mixture, because with this the telematics information we have these unobserved factors that we don't have now. So and this could be an idea, use all this information. But if you don't have this information, one possible solution is use a finite mixture that gives some information about these unobserved factors.
More questions? No? Thank you very much.
Yeah, thank you.
Okay, so with this presentation we finish the live streaming of the Congress. We are very happy about the great number of people who could follow the Congress sessions on streaming. We hope that all of you enjoy it. And finally, before we continue with the last presentation, we would like to thank again all the speakers and all the participants for their contribution to the Congress. Okay.